Good afternoon, everyone. So we'll continue with the applied optic courses on this online lecture series. And now in the second section, what we will be covering is more about LEDs, basic principles of LEDs, characteristics and application of various kind of LEDs. Then we'll jump into lasers. Some of the acknowledgements of the books that are recommended to study. A lot of these parts have been covered by SMBC and senior activity. Now, let's try to understand that we don't really see the whole spectrum of the light. So if you consider the whole spectrum of electromagnetic radiation, then there is only this much, which is a visible spectrum, which has these 7 colors. Now, not everything is like most sensitive to our eyes, and if you consider then with the eye sensitivity, then this is the region which has the highest sensitivity. So when we are building up LEDs, we need to be thinking about these parameters. Now, the effectiveness of light for stimulating the human eye is driven by the relative eye sensitivity, a luminous, which is strong function of wavelength. The maximum sensitivity of the eye is at 0.555 pm, and the value of this falls nearly zero at the boundaries of the visible spectrum, 0.4 up to 20. So in case of color of the red or violet eye sensitivity is the lower compared to green, and it takes higher intensity to achieve similar brightness as observed by human eyes. So that's the aspect we need to understand for building LEDs. We covered a detailed understanding about recombination process. Now we need to understand some more while studying LEDs, that from valence band and conduction band, from conduction band to valence band, the transition of electrons, they can happen in terms of interband, so from one band to another one, it can transit. The transitions can involve chemical impurities or physical defects. So defect centers can actually work as recombination centers. And there is also intra-band transition. Within the band, you can also have transitions. Now, the optical process for intra-band transitions between a photon and electron in a solid makes LEDs. So if you have like this He, which is a photon coming in, and it's get absorbed, then it goes to the conduction band. Whereas with a spontaneous emission, it gives away this photon also. So that is used for LEDs. It could be stimulated also. So for lasers, we use this stimulated one, this mechanism. And we create this with the help of the incoming photon that stimulates the emission of another similar photon by recombination, giving out the net of 2 photons which are coherent. The optical process for the interaction between photon and an electron in a solid is also interesting, because either for photon absorption and emission, the conventional theory for optical transition between the valence and the conduction band of a direct bandgap material is based on a case selection rule. So some of this I've discussed in the previous class, that for this kind of a transition, we really need to take care of the conservation of momentum. So the wave vector k1 of a valence band wave function and the wave vector k2 of the conduction band
must differ by the wave vector of the photon. Since the wave vector of this electron is much larger than that of the photon, the case selection rule is generally written as K1 is equal to K2. The allowed transition then between the initial and final states of the same wave vector and are called direct and vertical transitions. When the conduction band minima are not at the same value of K as the valence band, the existence of the photon is necessary to conserve crystal momentum, and the transition is called indirect. The radiative transition in indirect bandgap materials are much less probable. To encourage light emission in indirect bandgap semiconductors, special type of impurities are induced. The wave function change and the K selection rule does not hold. The modification of bandgap can be done by alloying. That is why we have materials like gallium arsenide phosphide. So they act, so they take care of the theories that we discussed in the last slide.
Now, if we have to define the energy released during the recombination process, we assume that the band-to-band recombination corresponds to the energy of the band gap. In practice, the electrons and holes reside slightly above or below their band edges on the conduction and the valence band respectively due to thermal energy when the temperature is above absolute zero. As a result, the photon energy emitted would be slightly larger than the bandgap energy. For the spectrum of the spontaneous emission near the band edges, the energy of the emitted photon is governed by this relationship. In this, the joint dispersion relation, m star is basically reduced effective mass. Then if we want to have an idea about the emission spectrum, it basically comes out like this, which translate into a spectrum width in wavelength, this one. Now the emission spectrum in real life looks something like this for a gallium arsenide diode at different temperatures. So you can already understand temperature does make a shift in the emission. The type of illumines may be distinguished by the source of input energy. One is the photoluminations involving excitation by optical radiation, cathodolumination by electron beam or cathode ray, radioluminance by other fast particle or high energy radiations. Electroluminance is what we're going to discuss here by electric field or current. Maybe we'll just skip that part. In electroluminance, optical radiation obtained by injecting minority carriers into a vicinity of a semiconductor field junction where radiative transition take place. Electroluminance may be excited in a variety of ways, including injection, intrinsic excitation, avalanche, tunnel process. The injection electroluminance is by far the most important method of excitation. When a forward bias is applied to a PN junction, the injection of the magnetic carrier across the junction can give rise to an efficient radiative current combination, since the electronic energy can be converted directly to the photon. For intrinsic excitation, a power of a semiconductor like zinc sulfide, is embedded in a dielectric, like a plastic or glass, subjected to an alternating electric current, a field, at frequencies in audio range. Electromagnetism usually occurs. Then generally the efficiency is low in this kind of a mechanism. It's mainly caused by the impact ionization of acceleration of electron and the field emission of the electrons from trapping centers. Whereas for an avalanche excitation, a p-n junction or a metal semiconductor barrier is reverse biased. For an avalanche breakdown, the electron-hole pairs generated by the impact ionization may result in emission of other interbond, which is an avalanche emission, or intravon, deaccelerated emissions. Now, the electroluminescence can also result from tunneling in forward bias or reverse bias junctions, when a sufficiently large reverse bias is applied to a metal semiconductor barrier on a p-type degenerate semiconductor. For example, holes at a metal site can tunnel into the valence band of the semiconductor and subsequently take a radiative recombination with electrons that have tunneled in opposite direction from the valence band to the conduction band. Let's get into the detail of light emitting diodes. LED is a semiconductor p-n junction that, under proper forward bias conditions, can emit external spontaneous radiation in the ultraviolet visible infrared region of the spectrum. Electroluminescence was first discovered by Raun in 1907. So he used silicon carbide substrate. Detailed experiments were further, it happened until 1930. Much higher quantum efficiencies were reported for direct bandgap materials like gallium arsenide. Significant advancements were further made in indirect bandgap materials, introducing isoelectric impurities. These studies had profound impact on the commercial LEDs made from indirect bandgap gallium arsenide phosphate and gallium phosphate. Most recently, a major advancement was made in indium gallium nitride, used to produce blue and ultraviolet portion of the spectrum, which had not been possible before. So that is where there was another Nobel Prize in 2016. The application of LEDs are in display, illumination, replacement of the traditional incandescent light bulbs, light source for optical fiber combination system, communication systems. Now, if we compare, then we already see that LEDs are definitely the most efficient among other options. Whereas the artificial light consumed about 8% energy and 22% of the US electricity. The energy cost is estimated to be $50 billion annually, which is $200 per capita. If we do a survey of the light bulb technology performances, obviously the luminance efficiency is found best for LEDs. OLEDs, which are the organic LEDs, are the new technology for green displays. So TVs and the PC displays, which is account for almost 1% of the US electricity usage, have started using OLEDs, which is way efficient and in using like power. Now, if we have to think in detail about light emitting diodes, the basic idea comes from a silicon p-n junction diode. similar to like BGTs, heavily using very long minority carrier lifetimes in silicon. In LEDs, we want all the excess carriers to recombine, and to do so, creating a photon of light. We want asymmetrical long base operations. What you get out of that is a cool, efficient source of light, which is extremely tough with extremely long lifetime, can be turned on and off very quickly and modulated at a very high data rates. The light emitting diodes, a typical spectra if you think about for a gallium arsenide phosphide, like the red LEDs, the important spectra to compare with the LED spectrums, with the human response of eyes, can be found in this for various kind of outputs. You think about the historical perspective of LEDs. It's drastically changed from 1990s, particularly because of many new materials which developed red-blue lasers. Then further, the improvement of the packaging technologies, development of wafer bondings, and further taking advantage of the advancement of many other technologies. The few of the design issues that needs to be solved, that needed to be solved in making LEDs were choosing the right semiconductor. You need efficient radiation recombination of excess carriers, emission at a right wavelength, the color that you're choosing, getting the light out of the semiconductor. So overcoming the total internal reflection and reabsorption, packaging the diode, good light extraction and beam shaping, good heat sinking for high intensity applications. Light emitting diodes and laser diodes today use materials for various colors like red, amber, blue, white, and they're used for CD players, fiber optics, pointers, printers, many other things. If you think about the device structure, then basically it's a PN junction. So if you think about a gallium arsenide, a PN type, in forward bias, minority carriers are injected from both sides of the junction. At the vicinity of the junction, there is an excess of carriers over the equilibrium value and recombine with one another. If a heterojunction is utilized, heterojunction is basically the two metals are not same. Like on the top image, you have gallium arsenide both sides. Here you don't. In this case, excess carriers of both types are injected and confined at the same place. The number of the excess carriers can be significantly increased. Increased carrier concentration, the radiator recombination lifetime is shortened, leading to more efficient radiative recombination. The central rear is undoped. So it's similar to the eye layer in a silicon solar cell, where a lot of recombinations actually take place in the eye layer, whereas the P and N type of carriers are actually injected within the eye part, and where they can effectively increase the recombination. While we think about the materials, as we mentioned before, it depends on the wavelength, that is the color we want. So various of these materials do have a particular wavelength that they target for LED. For photonic communication requiring data rates of 100 to 200 MB per second, With multimode fibers with tens of microvolts, LEDs are usually the best choice. The LED configurations are being used for photonic communications also. Now, then we also need to think about the design aspect of these LEDs, which could be as a surface emitter or edge emitter. The cross-section drawing of the typical gallium aluminum arsenide double heterosection emitters are given here. And in this structure, X greater than Y provide both carriers confinement and optical guiding. If you go to the next image, the energy band diagram showing the active region and the electron and hole barriers which confine the charge carrier to the active layer. The variation in the refractive index, the lower refractive index of the material in the region 1 and 5 creates an optical barrier around the wavelength because of the higher band gap energy of this material. The surface emitting LEDs basically active region is limited to a circular cross section that has an area compatible with the fiber core or face. So we're talking about putting this LED into a fiber optics. Edge emitting LEDs are probably found most commonly. The output beam is Lambertian in a plane of injection and highly directional perpendicular to the injection. They have a higher quantum efficiency and fast response. If we think about the spectral width of LED type, these both LED types, then we find that the surface emitting LEDs have a higher width than the edge emitting ones. So the bandgap of the materials and the ambient temperature determine the emission wavelength of LEDs. So these are the materials with the corresponding wavelengths that are used. And we also have a schematic of LED. Let's get into further detail of light source materials. Most of the light sources are basically 3 to 5 ternary and quaternary compounds like gallium, aluminum, arsenide. Now if you vary the X, it's possible to control the band gap of the energy and therefore the emission of the wavelength over the range of 800 to 900 nanometers. The spectral width is around 20 to 40 nanometers. Indium gallium arsenide phosphate by changing X from this range and Y approximately by this. The emission wavelength can be controlled over the range of 920 to 1600 nanometers. The spectral wavelength variation from 70 nanometer to 180 nanometer when the wavelength changes from 130 nanometer to 1600 nanometer. These materials are lattice matched. Now, we also need to understand, and this was discussed before, the direct and indirect band gaps. Various dopants are added to a PN junction of gallium arsenide to get emission over a wide range of colors. Gallium arsenide is preferred over semiconductors like silicon, germanium, as it's a direct bandgap material. In a direct bandgap material, the bottom of the semiconductor band lies directly at the top of the valence band. The energy of the electron in the conduction band with the zero of the energy being at the top of the valence is given here. The gallium arsenide is a direct bandgap material with the bandgap of 1.42 electron volt. The band structure for gallium arsenide is shown here. Other direct bandgap materials are indium phosphide, indium SPG, zinc sulfide, zinc selenide, etc. Compound semiconductors, a wide variety of band gaps, a majority are direct band gap, which are the most efficient ones. Now there are some compound semiconductors also, like gallium arsenide, which are extremely effective for using as LED materials, like gallium arsenide phosphide and aluminium indium gallium phosphide. See, these are used for red LED, the lattice matching with the gallium arsenide and then transferred to the gallium phosphide substrates. Similarly, amber color is also developed. Green. Now, the aspects for each of the material and their history may also be interesting in some parts. The main important part is probably the wavelength that they're operating, which color they can yield. So in case of gallium, aluminium gallium arsenide, which happened to start from 1960, they actually give out a range from red to infrared. For indium, aluminium, gallium phosphide, they cover red, orange, yellow, and green. Indium gallium nitride does have many other advantages, and it also covers green, blue, and violet. Gallium arsenic phosphate, from infrared to middle of the visible spectrum, they can cover. Now, another important aspect is efficiency in a device. The internal quantum efficiency, to understand, for a given input power, the radiative recombination process are in direct competition with the non-radiative ones. Each of the band-to-band transition and the transition via traps can be either radiative or non-radiative. Examples of the non-radiative band-to-band recombinations are those in indirect bandgap semiconductors. Examples of the radiative recombinations via traps are those via isothermic levels. The internal quantum efficiency is the efficiency of a converted carrier current to photons. So it's basically the ratio between number of photons emitted internally and the number of carriers that's passing the junction. It can be related to the fraction of the injected carrier that combine radiatively to the total recombination rate, and may also be written in terms of their lifetimes. Some of this thing we discussed during the first class. The concept about the carrier lifetime, radiative and non-radiative recombination rates and other things. For low-level injection, the radiative recombination rate in a p-side of a junction is given by this, where REC is the recombination coefficient and delta N is the excess carrier density, which is much larger than the minority carrier density in equilibrium. So REC is a function of the band structure and temperature. Its value would be very small for indirect bandgap semiconductors. For low-level injections, the radiative lifetime is related to recombination coefficient by this equation. For a high-level injection, this would actually decrease with change of concentration, carrier concentration. So in double heterojunctions LEDs, the carrier confinement increases the delta N and delta tau. The tau is reduced to improve the internal quantum efficiency. The non-radiative lifetime is usually attributed to traps or recombination centers, whereas sigma is captured cross-section. It is evident that the radiative lifetime tau needs to be small to yield high internal quantum efficiencies. The external quantum efficiency is also important. Considering for LED application, the important aspect is light emitted external to the device. For this, the optics inside and outside of the device has to be considered. The parameter to measure the efficiency of getting a light out externally is the optical efficiency, sometimes called the extraction efficiency. With this factor in, the net external quantum efficiency can be given by the number of photon emitted externally, number of carriers passing in the junction, across the junction. So the optical efficiency is also important when we consider the Snell's law, which states that the direction of the light before and after the interface is governed by this equation. Then it also alters the optical efficiency. To conclude with the LEDs, it does have a few drawbacks, like it has a large line width, large beam width, low output power, and low conversion efficiency. Most of these problems are solved by laser. The advantages of LED are immense. The ones which we'd like to highlight is robustness and its linear.